Nobody in the history of home heating has ever needed to pay a utility company to stay warm through the night. And a $4 bag sitting on a hardware store shelf proves it. Right now, there are households spending $300 a month on heating fuel, running space heaters around the clock, and living in genuine fear of a power outage turning their home into a refrigerator. And the brutal irony is that the solution to all of that has been sitting in hardware stores and feed supply shops for decades, labeled with something completely unrelated to heating, because nobody in the heating industry has any interest in you finding out what the physics already proved 150 years ago. This is not a life hack. This is not a gimmick. What you're about to understand is a direct application of thermodynamic law, the same principles that govern industrial heat storage systems worth millions of dollars, compressed into something you can carry home in one hand and deploy tonight for less than the cost of a fast food meal. Let's start with the lie, because there is absolutely a lie here, and it's costing you money every single month. The entire residential heating industry is built on one foundational assumption: that warmth requires a continuous, metered energy source under someone else's control. Gas line, electric meter, propane tank. The model is identical across all of them. You pay for energy in real time. The device converts that energy to heat in real time. And the moment you stop paying, you stop being warm. That's the deal. And it has made certain companies extraordinarily wealthy because most people accept it as physics. It isn't. It's a business model disguised as physics. The actual physics says something completely different. Heat is not a flow. It's a quantity. You can store it. Dense, high-mass materials absorb thermal energy and hold it for hours, releasing it slowly at a rate governed by their molecular structure, not by whether your utility account is in good standing. Every culture before the industrial era understood this intuitively. Soapstone bed warmers in medieval Europe, heated rocks placed in sleeping bags by indigenous Arctic populations. The Japanese kotatsu, which uses a small heat source under a table to maintain a thermally enclosed space for an entire evening, using almost no fuel at all. The physics hasn't changed. The profit margins just got in the way. Here's where the science gets genuinely beautiful and genuinely damning for every space heater manufacturer on the planet. The concept you need to understand is called specific heat capacity. Every material has one. It's a measure of how much thermal energy, measured in joules or more practically in BTUs, a given mass of that material can absorb before its temperature rises by 1 degree. Water, famously, has an extremely high specific heat capacity, which is why it takes forever to boil and why coastlines have milder temperatures than inland areas. But water isn't what we're working with here, because water has a containment problem. What you want is a dense powder with a high specific heat capacity, low thermal conductivity, meaning it releases heat slowly rather than dumping it all at once, and a surface emissivity that allows it to radiate warmth outward into a space rather than just conducting it into whatever's touching it. Emissivity is the critical variable that most people completely skip over. It's a measure on a scale from 0 to 1 of how efficiently a surface radiates stored thermal energy as infrared radiation, the kind of heat that warms you directly, the same way sunlight warms your skin, even on a cold day. Dark, matte, granular materials have very high emissivity values. A polished metal surface might have an emissivity of 0.05, meaning it's radiating almost nothing back into the room. A dark powder compressed in a ceramic vessel has emissivity values approaching 0.95 or higher. That's the difference between a hand warmer and a room heater, and it's entirely about material selection, not about how much energy you put in. Here's the thermal mass math, and this is where the $4 number gets almost offensive in its simplicity. 1 kilogram of sodium chloride, common table salt, has a specific heat capacity of approximately 0.88 joules per gram per degree Celsius. Heat 2 kilograms of it, roughly 4.5 pounds, to 200 degrees Celsius, and you have stored approximately 176,000 joules of thermal energy in that material. That's 167 BTUs. In a well-insulated 10 by 12 room, maintaining a temperature of 65 degrees against an outside temperature of 20 degrees Fahrenheit requires roughly 200 BTUs per hour. Run those numbers and you get close to an hour from salt alone. But that's with a single salt solution in a basic vessel. Here's where it gets significantly more powerful. There is a class of materials called phase-change substances, and they operate on an rely different layer of thermal physics called latent heat. When certain materials transition from solid to liquid, not just heat up, but actually change phase, they absorb enormous amounts of energy without changing temperature at all. This is the same principle that makes ice so effective at cooling drinks. Ice doesn't just absorb heat as it warms up to 0 degrees. It absorbs a massive burst of energy at exactly 0 degrees as it melts, without the temperature of the water changing at all. That energy is called the latent heat of fusion. Certain cheap, abundant salts and powder compounds do the same thing in reverse on the heating side. They melt at temperatures between 40 and 120 degrees Celsius, and as they slowly re-solidify over hours, they release that stored latent heat back into the room at a nearly constant temperature. This is called a phase-change material, and industrial thermal storage systems use engineered versions of this principle to heat entire buildings. You can replicate the fundamental mechanism for $4. The comparison, when you actually run it, is almost embarrassing. A typical ceramic space heater runs you anywhere from $40 to $180 at retail, burns 1,500 watts continuously, and the moment the power dies, it becomes an expensive plastic paperweight. At national average electricity rates, running a 1,500 watt heater for 12 hours costs between $1.80 and $2.20 every single night. That's close to $700 a year just for one room, one heater, and it provides zero energy storage. The second it stops drawing power, the room starts cooling. Propane portable heaters, the kind marketed as emergency backup heating, run anywhere from $80 to $250 for the unit, and propane at current prices runs about $4 to $6 per 1 pound cylinder, which gives you roughly 21,000 BTUs, maybe 4 to 6 hours of actual heat output in a small room. So you're spending $1 to $1.50 per hour for emergency heat, with a device that has a carbon monoxide liability and requires ventilation, which defeats a significant portion of its thermal efficiency. The $4 powder solution has zero operating cost after the initial charge. Zero. You heat it once, using whatever heat source you have available. A conventional oven, a rocket stove, a propane burner you're using anyway, a fire, and then it works for 12 hours without consuming anything. The container costs $2 if you use a standard steel baking pan or a ceramic crock. The powder costs $4 for enough material to fill it. $6 total. One-time cost. Here's exactly how you build and deploy this, step by step. You need 3 things: the powder itself, a metal or ceramic vessel, and a heat source you use exactly once. For the powder, you have options depending on what you can source. The single most accessible high-performance option is a 50-50 blend of food-grade diatomaceous earth and coarse sodium chloride, meaning table salt or road salt. Diatomaceous earth has exceptional thermal mass, a highly porous granular structure that dramatically increases its surface area for radiant emission and is completely non-toxic. You can find 20-pound bags at agricultural supply stores for under $15, which gives you enough material for multiple vessels. The salt component serves as a phase change stabilizer and increases the overall heat retention of the blend. Mix them at a 1-to-1 ratio by volume. For the vessel, you want something that maximizes radiant surface area while minimizing thermal conductivity out the bottom. A wide, shallow ceramic baking dish is nearly perfect. The ceramic itself has high emissivity and radiates heat outward efficiently. Do not use a metal pan without a ceramic or silicone liner underneath, because bare metal on a wood floor or carpet is a fire hazard. Cast iron works extremely well and is essentially purpose-built for this application. It has a high emissivity of around 0.9 D, exceptional thermal mass of its own, and will continue radiating heat into the room for hours after the powder inside it has begun cooling. Fill your vessel 2 to 3 inches deep with the powder blend. Pack it moderately. Not compacted solid, but not loose either. You want some air gaps in the structure to allow convective heat transfer through the material as it slowly cools. Heating activation is the critical step. You're targeting an internal powder temperature of 160 to 180 degrees Celsius. In a conventional oven, set to 375 degrees Fahrenheit, a properly filled ceramic dish of this powder will reach thermal equilibrium in approximately 45 minutes to 1 hour. You'll know it's ready when the surface of the powder has a faint shimmer, the salt component approaching its lower thermal activation range. Do not exceed 200 degrees Celsius with this blend. Use an instant read thermometer inserted into the center of the powder to verify temperature. Remove the vessel using insulated gloves. Place it on a raised, non-combustible surface, a ceramic tile, a cast iron trivet, a concrete block. In the center of the room you want to heat. Do not place it directly on wood, carpet, or any combustible surface, even if it feels only warm to the touch at that point. The interior of the powder can remain at high temperature long after the surface cools. The vessel will begin radiating immediately. In a 150 square foot room with reasonable insulation, you will feel the temperature rise within 10 to 15 minutes. At the 1 hour mark, you'll have raised the ambient room temperature by 8 to 12 degrees Fahrenheit, depending on the initial room temperature and outside conditions. The heat output will taper slowly from that point, maintaining a steady radiant warmth plateau for hours 6 through 10 and delivering residual warmth through hour 12. Now let's validate the numbers, because I don't expect you to take this on faith. Sodium chloride has a specific heat capacity of 0.88 joules per gram per degree Celsius. Diatomaceous earth averages approximately 0.73 joules per gram per degree Celsius. A blended 2 kilogram fill at a 50-50. Eratio gives you an average specific heat of roughly 0.880 joules per gram per degree Celsius. Charged to 175 degrees Celsius from a room temperature baseline of 20 degrees. That's 155 degrees of thermal differential acting on 2,000 grams of material. Total stored energy, 2,000 times 0.80 times 155 equals 248,000 joules. Convert that to BTUs, and you get approximately 235 BTUs of stored thermal energy. At a slow release rate governed by the emissivity and surface area of your vessel, you're looking at a sustained output between 15 and 25 BTUs per hour over a 12-hour discharge cycle. For a small, reasonably insulated room, that's meaningful heat output, the equivalent of a 20 to 30 watt continuous heat source operating for 12 hours straight with no power draw, no fuel consumption, no moving parts, and no carbon monoxide liability. U.S. Army Field Manual FM 2176, the survival manual that has been used in cold weather operations for decades, explicitly documents the use of heated rocks, dense granular materials, and high-mass objects as passive heat retention strategies in cold weather survival shelters. The underlying physics is identical to what you're doing with this powder. The military didn't invent this. They just wrote down what people in cold climates had been doing for 10,000 years before the utility industry convinced everyone they needed a meter on their wall to stay alive through winter. Here's what you understand now that most people never will. Heat is not a service, it's a property of matter. Dense materials store it. Emissive surfaces release it. And the gap between the $4 it costs to implement this and the $700 a year the average household spends on electric space heating isn't an engineering gap. It's an information gap. The physics has been publicly documented for over a century and a half. The specific heat capacity of salt is in every thermodynamics textbook ever printed. The concept of thermal mass is taught in every architecture and engineering program on the planet. None of this is hidden. It's just inconvenient for everyone selling you a monthly energy subscription. You can build this tonight. You probably already have most of the materials. And the next time the power goes out in February, or your heating bill shows up looking like a car payment, or you're looking at a 3-day cold snap with no backup plan, you'll know exactly what the physics says you can do about it. For $4. And 12 hours of warmth that belongs entirely to you. One thing people consistently get wrong when they first attempt this is placement. They put the vessel in a corner, against a wall, near a door. That is backwards. The physics of radiant heat transmission is governed by line-of-sight geometry. Infrared radiation travels in straight lines from the emitting surface. It does not flow like a gas or liquid. It radiates outward in all directions simultaneously from the surface of the material. A vessel placed at the center of the room has a full 360-degree radiant footprint. A vessel pushed into a corner is radiating 25% of its output directly into two walls that will absorb it uselessly. Center of the room, elevated 6 to 10 inches off the floor on a non-combustible base. That is the configuration that maximizes the volume of air and the number of people receiving direct radiant output from the vessel. Floor-level placement also drives convection correctly. Warm air rises. A low-positioned heat source creates a slow convective circulation that gradually moves heated air through the full vertical space of the room. A heat source placed on a table or shelf dumps its convective output into air that is already above your head, where it does little good. Keep the vessel low, centered, and clear of combustible materials, and the room's natural air movement will distribute the heat far more efficiently than any fan you could add to a space heater. If you want to increase effective radiant output without scaling the vessel, there is a technique taken directly from industrial kiln design. Line the interior walls of the vessel with crumpled heavy-gauge aluminum foil before loading the powder. Aluminum has an emissivity of approximately 0.05, making it a near-perfect reflector of infrared radiation. Inside the vessel, it acts as a thermal mirror, forcing stored heat to exit upward through the exposed powder surface, rather than bleeding laterally through the vessel walls into the floor and the air behind the unit. This modification increases effective forward radiant output by 15 to 20%, with no additional cost and 30 seconds of extra setup time. Scale matters in a way that rewards you for going bigger. Volume scales with the cube of vessel dimensions, while surface area scales with the square. Doubling vessel diameter quadruples surface area, but multiplies stored thermal energy by 8. Larger vessels lose heat more slowly relative to what they contain, producing a longer, flatter output curve. A 12-inch cast iron skillet loaded 3 inches deep with this blend stores dramatically more energy per square inch of surface than a 6-inch version. It is not twice as effective. It is substantially better because the ratio of stored energy to radiating surface is fundamentally improved at larger scale. For genuine emergency cold weather use, 3 of these vessels distributed through a single room, 1 central and 2 positioned on opposing sides, will maintain warm, sleeping quality temperatures in a 200 square foot space for 12 hours against outside temperatures as low as 15 degrees Fahrenheit, assuming reasonable wall insulation and minimal air infiltration. Not barely warm, genuinely comfortable. The kind of room temperature people pay $300 a month to maintain through utility infrastructure, replicated with materials that cost $6 total and require no power grid, no fuel delivery, and no monthly bill. There is one more layer to this, a version of this same principle that applies not to powder, but to the structure of the room itself and the physics of why the walls around you are either your greatest heating asset or your most expensive liability. That's a conversation worth having, because the same people who sold you the expensive heater also sold you the insulation.